RCP-28. You are looking at a narrow trail of newborn stars stretching across space for 200,000 light-years. The line is thin and straight, as if someone dragged a bright thread through the dark. Telescopes first found the strange band in deep imaging and called it puzzling. Later, infrared spectra revealed shock signatures at the tip of the trail that do not match ordinary galaxy debris. Here is what researchers propose. A supermassive black hole was ejected from its home. It is moving fast enough to slam into diffuse gas. The gas hits the shock and collapses into stars behind the moving hole. That creates a starry wake, like a boat cutting through water. The idea sounds cinematic. The evidence is not just pretty pictures. Spectra show fast-moving gas and line ratios that match shock models instead of gentle starlight. Observers tested the speed. One team reported a discontinuity in velocity across the tip approaching 1,000 kilometers per second. If that holds, the black hole is sailing nearly free of its galactic center. It would carry any bound gas and its accretion disk with it and stay visible as it runs. That is why this case is one of the clearest electromagnetic hints that supermassive black holes can be unbound. Not everyone agrees. Other astronomers pointed out that an edge on galaxy or tidal debris can mimic a thin stellar line. A careful rotation model could explain some of the motion. That disagreement matters because the interpretation changes everything we conclude about how often galaxies lose their central black hole. Some results point one way, some experts read the same light in another way. The follow-up observations are the part that changes a mystery into a test. Observers trained a powerful infrared spectrograph on the bright tip of the trail. They mapped emission lines across tiny angles and found a sharp jump in velocity right where the starry tail converges. The jump reads like a fingerprint of shock. The reported change was about 600 kilometers per second across a very small region. Later analysis interpreted the speed of the presumed black hole itself as roughly 954 kilometers per second relative to its galaxy. Those numbers matter. A speed near 1,000 kilometers per second can carry a black hole far from the galaxy center, and possibly out of the galaxy entirely. The measurements also included diagnostic line ratios that match fast radiative shocks rather than the slow motion of tidal debris. In plain language, the light looks like gas hit hard and heated quickly as a massive object passed through. That is the payoff. The imaging is striking. The kinematics and the shock chemistry line up with a moving, heavy object. Still, the debate remains honest and alive. Other researchers showed that a slim edge on galaxy, or some forms of tidal stream, can mimic a narrow linear feature and can reproduce some velocity gradients when viewed at odd angles. Those models do not produce identical shock line ratios in every case, but they remind us to be cautious. So the story stands on a knife edge. Strong new data favor a supersonic candidate. Credible alternate models demand more tests. Other objects show very different clues. 3. C186. That bright dot in deep space sits far from the center where we would expect a quasar to live. Hubble imaging shows the luminous point separated from the galaxy light by about 11 kiloparsecs in projection. Spectra tell an even stranger story. The gas near the black hole moves toward us at about 2,000 kilometers per second relative to the galaxy. In simple terms, the inner engine and the galaxy disagree about motion. The emission from the broad line region is blue shifted by about 2,000 kilometers per second, while the narrow lines that trace the host stay put. High-resolution radio and X-ray data pin the galaxy center where the molecular gas and the stars are. Millimeter interferometers then mapped cold carbon monoxide and found the fuel for stars sitting with the galaxy, not with the bright quasar. That pattern is exactly what a kicked black hole would produce. If a merger sent the hole flying, it can carry its fast-moving broadline gas and its compact radio core away from the host. The host keeps its cold gas reservoir. its stars, and its narrow-line gas. Observers combined optical imaging, integral field spectroscopy, and CO mapping to build this case. Skeptics are careful. A chance alignment of two unrelated objects can mimic a spatial offset. Powerful winds from a quasar can shift broad lines without moving the whole. Complex late-stage merger dynamics can sculpt odd light distributions that confuse simple interpretations. Models show a true recoil needs a specific prior configuration. So it is rare but allowed. The cold gas maps are decisive or they are not. They tip the balance one way if they truly anchor the galaxy. Other observations will test that claim. The cold gas map is the punch that shifts the debate. Interferometer images show the molecular reservoir sitting with the host galaxy, while the bright quasar is offset. The gas mass estimated is about 80 billion times the mass of the Sun. That is a huge fuel supply anchored where the stars sit, not where the quasar light comes from. That observation is powerful. If the quasar were simply a bright knot in the galaxy, the cold gas would follow the light. Instead, the gas anchors the galaxy and the quasar looks displaced. Combined with the broad line blue shift of about 2,000 kilometers per second and the projected separation of about 11 kiloparsecs, this paints a consistent picture of a displaced central engine. Radio and X-ray data add context. The object lives in a cluster with a cool core. The radio jets show structure that may be asymmetric because the engine moved. Those asymmetries are subtle, but they are the kind of fingerprint a real kick would leave. Simulations show that reproducing the observed geometry with a gravitational wave recoil requires a rare prior configuration of spins and masses. But it is allowed by the physics. Still, caution is necessary. Strong quasar winds can shift broad lines. Chance alignments of unrelated sources can fool us. Late-stage merger dynamics can make the stellar light look off-center. For a convincing proof, observers need higher resolution mapping of molecular gas and better radio imaging of the jet base. JWST or ALMA, observations that pinpoint the motion of gas at tiny scales, would be decisive. Another candidate tells a different story, J0437 plus 2456. Most supermassive black holes sit still at the centers of their galaxies, like anchors holding everything in place. This one refuses to stay put. Astronomers at the Harvard-Smithsonian Center for Astrophysics found it moving at about 177,000 kilometers per hour. That is roughly 110,000 miles per hour relative to its own galaxy. The discovery came from a clever trick involving water. When water molecules orbit close to a black hole, they can produce a natural laser beam of radiolight called a maser. That beam is so precise that astronomers can measure tiny motions across cosmic distances. The team used very long baseline interferometry to watch 10 distant galaxies and found 9 black holes sitting peacefully where they belong. One did not. J0437 plus 2456 was drifting through its host like a boat cut loose from its mooring. The black hole weighs about 3 million times the mass of our Sun and sits roughly 230 million light-years away in the constellation Taurus. That distance makes the detection even more impressive. Measuring motion at that range is like watching a snail crawl across a continent from orbit. So why is this black hole on the move? 2 ideas compete for the answer. The first idea is a past merger. When 2 galaxies collide, their central black holes can spiral together and merge. The merger sends out gravitational waves that carry momentum. If those waves blast out unevenly, the newly formed black hole recoils like a cannon after firing. That recoil could explain the speed we see. The black hole might still be settling down after a cosmic collision millions of years ago. The second idea is a hidden partner. Perhaps J0437 plus 2456 is not alone. A second supermassive black hole could be orbiting nearby, but staying dark because it has no masser emission. The visible black hole would wobble as both orbit their common center of mass. Either explanation is extraordinary. A recoiling remnant proves that gravitational wave kicks really do shove black holes around. A binary system means two monsters lurk in the same galactic core waiting to merge. Follow-up observations are hunting for the answer. Radio telescopes are searching for signs of a companion. Long-term monitoring will check whether the velocity changes in ways that match an orbit. For now, this restless giant stands as the clearest case of a supermassive black hole caught in motion inside its own galaxy. It may not have escaped yet, but it is certainly trying. Another runaway was caught in the act of doing something even more dramatic. At 2024 TVD. Sometimes a runaway black hole announces itself by eating a star. This one did exactly that, about 600 million light-years away. In early 2025, the Hubble Space Telescope captured ultraviolet and visible light from a violent flash. A star had wandered too close to a supermassive black hole and been ripped apart by tidal forces. Astronomers call this a tidal disruption event. What made this one special was the location. The flash did not come from the center of the galaxy. It came from a spot about 2,600 light-years off to the side. That offset is huge. Supermassive black holes are supposed to live at galactic cores, where gravity pulls everything together. Finding one that far off center is like finding a king living in a shed at the edge of his kingdom. The wandering black hole weighs about 1 million times the mass of our Sun. Meanwhile, a much larger black hole of roughly 100 million solar masses sits at the galaxy center where it belongs. So, how did the smaller giant end up displaced? Two ideas explain the setup. First, the wandering black hole could be a relic from a past galaxy merger. When galaxies collide, their central black holes do not merge instantly. One can be flung wide and spend billions of years drifting through the stellar suburbs. Second, a three-body interaction could have ejected it. If three black holes came together in a chaotic gravitational dance, two might pair up and kick the third out of the core. Either way, the tidal disruption event gave the game away. The shredded star produced shocks and outflows that glowed in ultraviolet and X-ray light. Those signals let astronomers pinpoint the position and prove the black hole was far from home. This is the first time an offset tidal disruption event has been observed. It opens a new window for finding wandering black holes that would otherwise stay dark. Future sky surveys will hunt for more of these cosmic murderers caught red-handed. The next candidate takes the idea of displaced black holes into even stranger territory, E1821643. It started with a spectrum that refuses to behave. In direct light, the broad hydrogen lines were shifted one way, while in polarized light, they swung the other way. That was not a small wobble. The effect pointed to a difference of about 2,100 kilometers per second between the central engine and the surrounding gas in some models. Here is what the team proposed. If the black hole itself moved relative to the galaxy, the light it carries and the light that scatters around it can show opposite shifts. Spectropolarimetry can see that because scattering picks out motion from a different angle. In plain terms, the polarized light gave a mirror view that implied the engine had a very large line of sight motion. Follow-up strengthened the mystery. High-resolution imaging and spectrostrometry found a small spatial offset between the narrow line region and the quasar continuum. The displacement was measured at roughly 80 to 130 milliarc seconds, which translates to a few hundred parsecs. Long-term monitoring measured reverberation lags and produced a black hole mass of order a few billion times the mass of the Sun. That mass is central because it sets how tightly the broad line gas can stay bound if the hole actually ran. put together, the numbers matter. A mass of a few billion suns and a required speed of about 2,000 kilometers per second mean the progenitor merger would need very particular mass ratios and very large, misaligned spins to produce such a kick. That is rare, but not impossible, according to numerical relativity. Scientists do not stop at a neat explanation. Others point to winds, complex scattering regions, or cluster interactions that could mimic some signatures. The next half will look at the detailed models that try to meet the parents of this runaway and test whether the numbers add up. The models are unforgiving. To get a remnant moving at the speeds implied by the spectroscopy and polarimetry, you need two black holes of similar mass and both spinning very fast. Bayesian reconstructions find the best fits when the mass ratio is close to unity, and the spins are large and tipped in unusual directions. In plain language, the parents must have been nearly twins, and they must have argued with each other in spin orientation just at the moment they merged. Numerical relativity backs the possibility. Simulations show that special spin alignments can create so-called superkicks. Under the right geometry, a few thousand kilometers per second is allowed. The absolute maximum depends on details, but published runs approach speeds of 4,000 to 5,000 kilometers per second in extreme, rare setups. That makes a kick of about 2,200 kilometers per second physically possible. Rarity is the rub. Gas-rich environments tend to align spins and suppress big kicks. Cosmological models tell us very large recoils are rare. You can get one occasionally, but the odds are low. That means the observational claim must be held to a very high standard. What would settle it? First, an independent spatial anchor, like cold molecular gas, at the galaxy systemic velocity. Second, a visible wake or shock trail in the surrounding medium. Third, radio jet asymmetries that match a moving engine. Fourth, direct proper motion over decades if the speed and distance permit. Finally, gravitational wave detections of massive black hole mergers by space observatories will give the cleanest parent parameters and make the story conclusive. The last clue does not come from light. It comes from ripples in space-time. The infinity galaxy. When two spiral galaxies collide head-on, they can create something that looks like the symbol for eternity. JWST found exactly that in archival survey data, and the shape was just the beginning of the surprise. Inside this cosmic figure, 8 astronomers counted 3 active supermassive black holes instead of the expected 2. 2 of them sit in the nuclei of the original colliding galaxies, right where you would predict. The third one floats between them in a vast cloud of ionized gas, like a wanderer caught between 2 kingdoms. That middle black hole weighs roughly 1 million times the mass of our Sun. It is actively feeding and glowing with the telltale signs of accretion, but it is not anchored to either galactic core. How did it get there? The leading idea involves direct collapse. In the chaotic environment of a major merger, dense gas can pile up and collapse straight into a supermassive black hole without first forming stars. That process could birth a heavy seed right in the collision zone. The alternative is ejection. Perhaps one of the original cores lost a black hole during an earlier 3-body interaction. The ejected engine then settled into the turbulent gas between the merging nuclei where it found fuel and started glowing again. Either explanation rewrites part of our understanding. Direct collapse in a merger would give strong evidence for the heavy seed theory of supermassive black hole formation. That theory tries to explain how the biggest black holes grew so fast in the early universe. Ejection plus recapture would show that runaway black holes can find new homes and restart their engines. The infinity galaxy is close enough and bright enough for follow-up. JWST can map the gas kinematics in detail. ALMA can look for cold molecular fuel. X-ray observatories can check for hard emission from each nucleus. Those observations will decide whether the middle black hole was born in place or kicked there from somewhere else. Either answer is a win for science. Another candidate pushes even further back in time. ZS7. The James Webb Space Telescope looked back to when the universe was only 740 million years old and found two supermassive black holes in the act of merging. That is the most distant black hole merger ever observed. The system was caught during cosmic dawn, the era when the first stars and galaxies were just switching on. At that time, the universe was a baby by cosmic standards. Finding two supermassive black holes already spiraling together rewrites what we thought possible. One of the black holes weighs about 50 million times the mass of the Sun. The other is likely similar, but harder to measure because dense gas obscures it. Together, they outweigh the central black hole of our Milky Way by more than 10 times. The discovery came from JWST near-infrared spectrograph. Astronomers saw dense gas moving at high speeds and highly ionized atoms glowing with the telltale heat of active accretion. Those signatures scream that two engines are feeding close together. And here's the twist. When this merger finishes years from now in cosmic time, it will release a massive burst of gravitational waves. The asymmetric blast will kick the newly formed black hole. Depending on the spin alignment that kick, could send the remnant racing through its young host, or even out of the galaxy entirely. ZS7 is a time machine that shows us the setup before the punch is thrown. It teaches us that the conditions for creating runaway black holes existed from the very beginning. Galaxy mergers in the early universe triggered black hole mergers that triggered gravitational wave recoils. The cycle started early, and it never stopped. Future space-based gravitational wave detectors like LISA will catch these ancient mergers directly. Until then, JWST gives us snapshots of the parents before they collide. A very different line of evidence confirms that gravitational wave kicks really happen. GW 200,129. The detectors recorded a signal that, when studied with the most advanced numerical surrogates, points to a remnant black hole getting a huge kick. Researchers translated the wave shape into motion and reported a median recoil of about 1,542 kilometers per second, with a broad, credible range that still leaves the number large. How did they do it? They used a numerical relativity surrogate waveform named NR-SUR 7DQ4. That model is trained on full general relativistic simulations of spinning, precessing mergers. It captures subtle wobble signatures that simpler models may miss. Then, a remnant surrogate mapped the inferred pre-merger masses and spins to the final speed of the merged whole. Together, these tools let scientists turn tiny features in the chirp into a three-dimensional kick estimate. Why the speed matters. A few thousand kilometers per second can carry a remnant right out of a small galaxy. Using the inferred kick distribution, the team calculated retention odds. For typical globular cluster escape speeds, the remnant almost certainly leaves. Even for dense nuclear clusters, the chance of retention becomes small. That means such a kick reshapes where black holes live and whether they can merge again in the same place. This is the moment gravity shows off in public. Still, the claim rides on model choice and on subtle parts of the data. Next, we will ask how robust the result is and what parts of the signal drive it. The big question is how much trust to put in that one event. The short answer is this. The kick inference is strong when you use a waveform that is built from full numerical relativity and when the data are treated carefully. But the claim weakens when you change models or when you change which detector data you include. Here is why. The signature that points to a huge kick comes from subtle modulation in the waves caused by precession. Some waveform models capture that wiggle better than others. The numerical surrogate used in the study was trained on many full simulations, and it finds the strongest precession. Simpler phenomenological models find less. That model dependence matters because the kick depends on the exact spin directions during merger. Then, there is data quality. one detector had a glitch in a narrow frequency band during the event. Removing that band or reweighting the data reduces the precession evidence. In plain terms, one small corner of the recording can shift the result for a single event. That does not mean the team made a mistake. It means the claim sits on a delicate balance between model and data choices. So how do you test it? First, rerun the parameter estimates with several waveform families and compare the kick posteriors. Second, run injection tests to see whether detector noise or gaps can mimic the precession signal. Third, compare the remnant inferences to population expectations. If many future events show similar behavior, then the picture becomes robust. There is also a clean path forward. Space-based detectors will measure massive black hole mergers with far higher signal quality, and they will give direct progenitor parameters. Those future measurements will either confirm that nature produces superkicks, often enough to matter, or they will show GW 200,129 was an outlier. A very different kind of runaway, one you can almost see, gives the next chapter a striking visual clue about what a displaced black hole can do to a galaxy, GW 190412. For the first time, astronomers did not just estimate a speed. They measured where the merged black hole went in 3 dimensions. Using subtle features in the wave, called higher-order modes, the team recovered both direction and speed of the recoil. Here is the quick version. When 2 black holes merge, they send out ripples in spacetime. Most of the signal is the loud, simple tone people know. But unequal masses and tilted spins add extra tones. Those extras are the higher-order modes. They are faint, but they carry information about the orientation of the system. This event had enough of those modes to be useful. Scientists used a waveform built from many full general relativity simulations. That waveform captures the higher-order modes and how precession twists the signal. They ran parameter estimation and then mapped the result to the remnant motion. The outcome is a directional posterior that points where the kick is pointing and a speed estimate that lets them compare that kick to escape speeds. The headline finding rules out very small kicks. In plain language, the data strongly disfavor kicks below about 50 kilometers per second for this remnant. That is important because typical globular clusters have escape speeds near that value. If the remnant got more than 50 kilometers per second, it likely left most small clusters. This is a breakthrough in using gravitational waves as real motion detectors. Next, we will peel back the uncertainties. We will ask how much the result depends on waveform choice, and on which part of the detector data carries the signal. The first question scientists asked was this: could a model choice or a noisy stretch of data fake the directional signal? They ran 3 checks. 1, they changed waveform families. They repeated the inference using independent models and compared the kick posteriors. The direction stayed centered, but the exact speed shifted depending on model details. That tells us the direction is the more robust piece of information, and the magnitude depends more on waveform systematics. 2, they performed injection tests. They injected numerical relativity signals into realistic detector noise, and then recovered them with the same pipeline. These blind tests show the method can recover direction reliably when higher-order modes are present at measurable strength. They also quantify typical biases and uncertainties. 3, they varied the data treatment. A known glitch affected a narrow band in one detector for a related event. Removing that band, or reweighting detectors, changed the strength of the precession evidence. For this event, the directional constraints survive reasonable data choices. But the evidence weakens if you cut certain frequency ranges. That means data quality matters. So where does that leave us? Directional information from higher-order modes is real for loud asymmetric mergers. Magnitude estimates are more model-dependent. If repeated events show the same pattern, then confidence will rise sharply. If not, this could be a striking but rare case that teaches us about waveform systematics and detector artifacts. Either way, the payoff is immediate. Knowing where a merged black hole goes in space changes whether it stays to merge again in the same place. That changes models of how the heaviest black holes form. A very different runaway nearly shouts at us in starlight, and we will look at it next. Superkicks. Numerical relativity showed something wild. When two black holes merge with the right spins, the merged hole can be flung away at speeds of thousands of kilometers per second. In some simulations, the remnant reaches several thousand kilometers per second, enough to escape even the largest galaxies. What creates that brute force? It is not a mystery engine. It is the way gravity radiates momentum. If the two holes spin in certain directions, the gravitational waves carry away more momentum one way than the other. Conservation of momentum makes the newly formed hole recoil in the opposite direction. Think of two figure skaters throwing their arms in a lopsided way and one skater being pushed across the ice. The numbers are striking. Early full general relativity runs predicted kicks of a few thousand kilometers per second in special, so-called superkick geometries. Later studies found hang-up kick effects that push maxima even higher when spin components line up in particular ways. Those are extreme and rare, but they are allowed by Einstein's equations. Why rarity matters. Gas-rich galaxies tend to align the spins before merger. Alignment reduces the chance of a huge kick. If spins stay random, large kicks become more common. So the probability of ejection depends on astrophysics before the merger, not on the math alone. Why observers care? If a merged hole escapes its galaxy, it cannot feed or merge again there. That changes how heavy black holes grow across cosmic time. The theory handed observers a clear prediction and an urgent task. Hunters switched to new strategies that can actually spot a black hole that has been thrown out of town. Checklist. If you want to find a runaway black hole, do these things in order. First, get a precise position. Use high-resolution imaging with space telescopes like HST or JWST. Confirm a luminous point source that is clearly off the stellar center. Second, measure motion in the light. Get spectra that separate broad-line gas from narrow-line gas. A persistent velocity offset between those two is a red flag. Third, map the cold gas. Use ALMA or NOEMA to find where the molecular reservoir sits. If the cold gas anchors the galaxy while the bright source sits elsewhere, you have a strong case. Fourth, check high-energy emission. Chandra or XMM can show whether an X-ray core sits with the offset light. Radio VLBI can locate a compact jet core to milliarc-second precision. Fifth, look for a wake or shock. Deep IFU spectroscopy, or JWST IFU cubes, can reveal shock ionization and velocity discontinuities behind a moving object. Avoid common traps. Dual or binary AGN can mimic offsets. Projection of two galaxies in the same sightline can trick you. Strong quasar winds can shift broad lines without motion. To rule these out, require multi-wavelength consistency. If radio, X-ray, millimeter, and optical all point to the same displaced engine, then alternatives shrink. Do simple timing checks. Repeat spectra over years to test for orbital acceleration. Use image registration tied to stars for robust astrometry. Run a jet symmetry test to see if radio lobes point back to the host center or to the offset core. If all checks pass, you have more than a headline. You have a direct probe of extreme relativistic dynamics and of how galaxies lose their most massive anchor. The next example is one that practically screams at telescopes with its star-forming tail.